Hey everyone, how's it going? Hey. Yeah, not bad, thanks. Not bad. Uh, Hi, good to see some old and some new faces. So today is going to be all about resolving forces, which is like a bread and butter thing that comes up all over your physics exam. Hi Leo, how's it going? Hey. Hey Laura. Yeah, I'm not bad. I'm not bad. Um I always I quite enjoy these YouTube sessions, so I'm in quite a good mood right now. um, it's also cool as a result of learning how to do these YouTube live streams. One of a conference that I'm involved in with like my physics research, we've now managed to get it to work completely online. So we're doing a complete like online conference on YouTube as well. So I'm really glad to have like learned how to do this stuff. I know, I think YouTube Live is really good actually. Like this is such a cool way to learn when like we're not allowed to be in the same place as our teachers, etc. Has everyone managed to kind of get outside a little bit now? Hmm. Yeah, it's definitely worth taking a little walk. It's that place that used to be good before the thing happened. Worries. I feel like especially not outside right now because of course for these sessions I have like a light set up and can't get the let the natural light in, so I have to like close the curtains and kind of feels like it's still nighttime here. Yeah, it's resolving forces is it's a tricky topic, but it's super important because it comes up everywhere. And often you won't even be kind of told that like a question is about resolving forces. They'll just kind of want you to do it just kind of naturally. So yeah, it's a really good thing to feel like you can get on top of. Um, Speaking of which, let's smash through and start having a look. So thanks everyone for coming. Um, Been really looking forward to doing this session. Hopefully you can all see this screen. So today is on resolving forces. Like I said, this comes up everywhere, bread and butter. We've got to know this stuff. So we thought it would be good to go through a few exam questions and check we all understand this together. So as always, if you have any questions, put them in the chat. I'd love to see them, and it'll be great to kind of have that back and forth. I'll be asking you questions throughout. Feel free to put your answers, and then I can see how everyone's getting on as well, and if everyone's getting it. Good. So let's smash through. Hi, Maria. Good to meet you. Okay. So as always, at the end of today, there will be a coupon giveaway for Snap Revise. So as you can see, today we're doing this from Snap Revise. Snap Revise is a company I work with. I'm head of physics at Snap Revise. We produce educational content. We produce like video courses, and we do lots of sessions like this at the moment. Web classes that you can come to and ask questions about things that you're confused about. So stick around to the end and there'll be a coupon code that we can give away for a discount. Good. Okay. So first question, let's smash in and have a go. Define a vector quantity and give one example. Good. So this is just a nice little warm up. What does it mean for something to be a vector? Give me an example. Give me your worst. What have we got? Good. Okay. A vector quantity has both a magnitude and a direction. Good. Okay, and then I'm wanting to see some examples here. What have we got? Vector has magnitude, vector has direction. Good. Which one of those does a scalar have, the magnitude or the direction? Good, and I'm seeing some nice ones. So displacement is a cracking example, velocity as well. Sorry, hay fever hasn't completely gone yet. Good, so some examples we could have given. We were asked for a example, but I'll put both of yours down. Velocity. Sorry. Okay, let's do it again. Velocity and displacement. Good. Yeah, momentum is another nice one, and acceleration is too. Good. Okay. Figure 3.1 shows a force F at an angle 30 to the horizontal direction. Okay, so this is another warm-up, another thing that we're going to need to answer some other questions. The horizontal component of the force F is 7 newtons. Calculate the magnitude of the force. Okay, so every force can be split up into components. So we can consider this force to be a sum of this vector, the vertical component, and this vector, the horizontal component. Good, well, this is a right angle. So we're told the horizontal component is 7 newtons. How can we figure out F? Okay, so what's the how are you figuring this out? I've seen a couple of mentions of SOHCAHTOA. So what does SOHCAHTOA tell me here? So I'm seeing a lot of answers that are very nearly right, but not quite. So that's why I want to know exactly what SOHCAHTOA says. So the K in SOHCAHTOA says cos theta equals adjacent over hypotenuse. So what's the hypotenuse here? The hypotenuse, that's the longest side of the triangle, that's F. Okay, what's the adjacent? That's the side that's adjacent next to or adjacent to the angle, and that's this 7 here, this horizontal component. So this tells me, and this is why we have to be careful here, this tells me that cos 30 degrees is equal to 7 divided by F, or F is equal to 7 divided by cos 30. So you see, this is very cheeky. Usually you know the big one, and then you multiply by cos 30 to get the horizontal component. Here we were told the horizontal component. Here we were told the horizontal component. And so we end up dividing by cos theta instead. So it's always good to kind of go back to the start and remember this formula. Cos theta is adjacent over hypotenuse. If you use this formula and you definitely check which one is adjacent and which one is hypotenuse, then you can't go wrong. Good, exactly. The horizontal component of the force, so that's this one here, is 7 newtons. Yeah, so this is a very cheeky question. Good, okay. So if you put this into calculator, you should find that F is equal to 8.1. Good, okay. So yeah, well done, everyone. Let's have a go at another example. So, okay, so now we'll start to kind of expand on things a bit more, get through the warm-up a bit. So, figure 5.1 shows the vertical forces acting on helium-filled weather balloon just before liftoff. Okay, so there's some forces, some kind of a wind as well. Okay. The balloon experiences an upward vertical force equal to 120 newtons. Good. Okay, this piece of information is in the diagram. We can ignore that bit now. The weight, and it's okay, the weight of everything is 90. The magnitude of the horizontal force provided by the wind is 18. Right, so there's a piece of information that they didn't put in the diagram for us directly. Determine the magnitude of the resultant force acting on the balloon and the angle this resultant force makes with the horizontal. Okay, good. So how can we do this? How do we add up these vectors together? Nice. So one thing we could do to start with is to find the net vertical force. Yeah, I like this. There's a few ways we could do this. So we have to make a choice. And I think finding the vertical force first is a good idea. So what's the vertical force? We know horizontal force is 18 newtons. What about the vertical force? Absolutely right. It's 120. Take away 90. These two forces are working against each other. Good. And what's the magnitude of this force? Well, as you say, 120 minus 90, that's 30. Okay, so how do I add together these two forces to get a resultant force? How do I add together two vectors? So there's two ways of thinking about this. It's probably kind of a vague question, but just like going really back to basics, one way of thinking about how to add vectors is to take the tip of one and put it on the tail of the other. And of course, that will indeed make the triangle that I expect you're all kind of thinking about already. So we've got a triangle with 18 on one side, 30 on the other. We want to find the length of this resultant vector. And what rule can we use there? In this triangle, we know that this angle is 90 degrees, so we can use Pythagoras to add these together. Now, I may have spelt that wrong, so sorry, Pythagoras. Okay, so let's call this C. C is equal to the square root of 18 squared plus 30 squared. And you should find that is equal to 35 newtons. And in fact, I saw that answer in the comments already. So that's good news. Good. Okay, what about the angle? How can I find this angle here, for example? Good, let's use SOHCAHTOA again. And SOHCAHTOA, tan theta is equal to opposite, which is 30, divided by its adjacent, which is 18. So we can find theta as tan inverse of 30 over 18. Wonderful stuff. Good. So the net force is 35. And if you plug tan inverse of 30 over 18 in your calculator and make sure you're in degrees, you should get 59 degrees. How do I know it's that angle? Good question. So let's take a look at this again and find the angle that this force makes with the horizontal. So it's true that that could, in principle, mean this angle theta or this angle here. I think when people say something like what angle is made with this line, they mean what is the smaller of the angles made with the line, because there's always two of them. And it's a good question, actually, but you would always choose the smaller of the two angles it makes with the horizontal. Yeah. Woo! Nearly had a catastrophe there. Yeah, so the angle with the vertical would be 31 degrees, 30, 60 to 90. Yeah, absolutely right, 31 degrees. Absolutely right, good. Okay, next question. A diagram shows a 250 kilogram iron ball being used on a demolition site. The ball is suspended from a cable at a point A and is pulled into the position shown by a rope that is kept horizontal. Cool, okay. The tension in the rope is 1,200 newtons. Cool, so we've been given this piece of information. Is there anything else we can put on the diagram? Yeah, it's 250. Okay, so this is 250 G because weight is equal to mass times gravitational acceleration. Good. Yeah, let's see. So in the position shown, the ball is in equilibrium. What balances the force of the rope on the ball? What balances the weight of the ball? So this is a bit of a weird one. They're not asking for any numbers. They're just asking, how is this happening? How is it staying still? So what force is balancing the force of the rope? In particular, is it all of the tension in the rope? So there's two, whenever things are balanced, there's always two directions we can interpret forces in. We can talk about the kind of vertical bits and we can talk about the horizontal bits. Now, because this thing is in equilibrium, this means that both the horizontal forces are balancing and the vertical forces are balancing. Now, the tension isn't really in either direction. So if we wanted to be really precise here and say what balances the force of the rope on the ball, I would say for I, the horizontal component of T. That is the tension in the cable. Good. So there's two different components to this tension, and what they're kind of asking for in these two different bits of the question is to check that we kind of understand that part of the tension in the cable is going into balancing the rope and part of it is going into part II. So what's balancing the weight? Which bit of the tension is balancing the weight? So there is a tension in the rope. The tension in the rope is this one here. There's a tension in the cable, which is this one here, this one which we don't know. Now for part II, all they're kind of looking for us to say is that the vertical component of T balances with the weight. Good, yeah. Now, part of the reason they're asking this is as a warm-up for what they next want to ask, because they're going to want us to calculate some of this stuff now. So let's take a look at the calculations. So we're asked to determine the magnitude of the vertical component of the tension in the cable and the magnitude of the horizontal component of the tension in the cable. Good. Okay. So first of all, this weight was equal to 250 G, wasn't it? Now, the horizontal component, let's split up this force into horizontal and vertical. There's a horizontal, there's the vertical bit. We know the horizontal bit of this tension must balance the tension in the rope. So the magnitude of the horizontal component must be 1,200. What about the magnitude of the vertical bit? The vertical bit absolutely must be balancing this weight. So that's absolutely right here, that the vertical component must be the same as the weight. So this should also be 250 G. Now, let's just check for I. 250 G is equal to 250 times 9.81, which is roughly equal to 2452 newtons. Good, absolutely right, good. And for the horizontal component, well, there really is not too much to say. It just needs to be 1,200. Okay. Given that we know these values here, you may be able to guess what we're asked next. So next we're asked to determine the magnitude of the tension in the cable. So we actually want to find T now. And we want to find the angle it makes to the vertical. So remember, we found these two components of this tension now. We found this component here, which was 2452. And we found this component here. And what was this component? This component was 1,200. So what are we being asked for? The angle with the vertical. So we're being asked for this angle here this time. And we're being asked for the magnitude. So first of all, for the magnitude, how can I figure it out? What rule are we using to find the magnitude here? Pythagoras, absolutely right. Good. Okay. So Pythagoras's rule says that T squared is equal to 1,200 squared plus 2452 squared. And this implies that T is equal to the square root of that stuff, which should be 2773 newtons. Good. Now for this part here, we need to somehow figure out this theta. Now to figure out this theta, and if we want to use trig stuff and these lengths that we know, we need to find one of the angles inside the triangle. So can anyone tell me what this angle here is? True, it's acute. In terms of this angle theta here, does this angle here have anything to do with theta? And what rule are you using to convince me that there's something similar about them? Yeah, these are actually equal. Absolutely right. This is a rule that you may have seen in GCSE maths. If I have two parallel lines and I have a line going like this between them, then this angle theta here must be the same as this angle theta here. Exactly, yeah, these are these alternate angles. Or sometimes they're called like the Z rule angles or something. So sometimes you do need to kind of pluck out this information from GCSE maths. So absolutely right. This angle here is also theta. Now, if we know that angle is theta and we know 2, 4, 5, 2 here and 1, 2, 0, 0 here, then how can we figure out theta? Well, let's use the Toa bit of SOHCAHTOA again. Tan theta is equal to the opposite to the angle divided by the adjacent. 1, 2, 0, 0 divided by 2, 4, 5, 2. Good. So this implies that theta, if you put this into your calculator, should be equal to 26 degrees. Good. Absolutely right. I'm seeing lots of 26s here, so that's great. Good. If you got the wrong answer, as always, check with radians. That can be a start, although, yeah, if you do theta inverse of this thing, you should get 26 degrees. Good. Okay. So well done, everyone, for that question. It's quite a long question, actually. I mean, had at least 4 parts. That's certainly something. Let's do something kind of different now. So figure 5.1 shows a person standing in a stationary lift. Now, I always think some of these lift questions where they get the lift moving and ask various things about the forces are some of the more confusing ones. So let's have a go at this. We've got someone standing in a lift. There are only 2 forces acting on the person. The weight of the person is 590 newtons. The vertical constant force acting on the person from the floor to the lift is R. Okay. Show that the mass of the person is 60 kilograms. Good. So how can I do this? How do I go from a weight to a mass? What's the formula? Good. I can see the formula here. To go from a weight to a mass, I need to use the fact that W is equal to mg. If W is equal to mg, we've been told W. We've been told the weight, which is 590. We just wish we knew the mass, and we do know gravitational acceleration. So m equals 590 divided by 9.81. And you should find that that is 60 kilograms. And in fact, they asked us to show it. So good. We got a mark here just for kind of recalling the formula for weight. So that's great. Now things kind of develop a bit. The lift starts from rest. It has a constant upward acceleration of 0.5 meters per second. Calculate the magnitude of the contact force R. So what do we reckon? Has anyone got any ideas for this question? Yeah, so it's going to have something to do with F equals ma. That's true. What type of force, which force is equal to mass times acceleration? Is it any old force? Is it the reaction force that's equal to mass times acceleration? Is it the weight? Is it something else? Good, the resultant force. Okay. Resultant force is equal to mass times acceleration. We know the acceleration. It's this thing. And we know the mass too. So the resultant force must be equal to 60 times 0.5. So 30 newtons. Okay, so what are the 2 forces acting on this person in the stationary lift? It's not like there's now a new force. So there's still the same two forces acting on this person. There's a weight and a normal reaction. Is the weight going to have changed? We can choose whatever directions we like inside the question because their answer just needs to be a magnitude. Good, so there's a weight and a normal reaction. So back when the lift was stationary, the reaction force was the same as the weight. That's the usual situation. Here, they mustn't be the same. Here, if we add together these two forces, they must give this resultant force because they're the only two forces on this person. So for this person to be accelerating upwards, that tells us that the reaction force will be bigger than 590. And in particular, we know there must be some net upwards force. That's this 30 here. So we know R minus 590. That's one way of us calculating the resultant force. It's the reaction force minus the weight. We know the resultant force must be equal to 30. So what does that mean for R? R must be equal to 620 newtons. Good, absolutely right. Good stuff. Well done. Good, okay. So, C, after a short period of acceleration, the lift travels upwards at a constant velocity. Explain why the force R is equal to the weight of the person when the lift travels at a constant velocity. So what do we reckon? Do we have any ideas for this section? When we're at a constant velocity, the force R is equal to the weight. Why is that? Yeah, what does Newton's first law say? Good. Good. So from, for example, Newton's first law, let me just write that in full. That's not a good abbreviation. Newton's first law. So what does this say? This says constant velocity implies resultant force, not just any force, the resultant force is equal to 0. What does that mean for us? Well, if the resultant force is equal to 0 and there's only two forces, they must balance each other out. So this implies reaction force must balance with the weight. Good. Nice one. Really nice answers. Good. It's in equilibrium. That's another great word you can use to describe this situation. Great. Okay. State and explain how the force R changes at the instant that the lift starts to decelerate. So first of all, state it, then explain it. So what's going to happen to R as the lift decelerates? Good, R is going to decrease. Now we have to explain it. So why is it going to decrease? Why is R going to decrease? Good, absolutely right. So how do we know that the weight is now bigger than R? Yeah, I guess it's because we have this deceleration. So R will decrease. Okay, R will decrease to cause this deceleration. Why is this? Well, for a deceleration, the weight must be bigger than the reaction force so that resultant force will be downwards. Good. Okay. So deceleration means a downwards force, which means that the weight must be bigger than the reaction force. Therefore, R becomes less than 590 newtons. Whereas previously it was 590 newtons because previously it was equal to the weight. So it absolutely must decrease. Absolutely correct. Well done. So let's have a go at one more question. Figure 3.2 shows the forces acting on a stage light of weight 120 newtons, held stationary by two separate cables. Our examiners love these questions. Two separate cables, classic. Different angles, weird angles between them. The angle between the two cables is 90 degrees. One cable has tension 70 newtons and the other has tension T. Okay. So state the magnitude and the direction of the resultant of the tensions in the two cables. So if I have these two forces and they're perpendicular to each other, can I try to find, first of all, the magnitude of the resultant force? How will I do this? So remember, this isn't really a vector addition at the moment. This isn't a resultant force because I've added these vectors like kind of tail to tail. So first of all, let's draw them in a better way. If you want to find the resultant, you've got to go tip to tail. Good, okay. So I don't know this thing here, do I? And I know this one here. Fine. Now, actually, I don't need to worry about too much of this for now. State the direction of the resultant of the two tensions in the cables. We don't actually have to do any of this working out. Why is that? What's special that we know about this situation? So we've been told that this object, this stage light, is stationary. So if it's stationary, what does that mean? It means that there is no resultant force acting on it. Now, there is one force, which is 120 newtons pointing downwards. So these two together must create a force which balances this force. So what must their resultant force be when I add them together? So it's just the resultant. So it's what do we get when we put these two tensions together? Well, these two tensions together must create a force which balances this weight. So they must also create a 120 Newton force, and it must balance this weight, so it must be upwards. This is all because the object is stationary. Good. Okay, so because this thing is stationary, we get a load of information for free, and they've checked that we can extract this information from the question. Now we're going to be asked to do some working out. Sketch a labeled vector triangle for the forces acting on the stage light. Hence determine the magnitude of the tension T. Okay, so we know full well that these two forces, when added together, should make a new force Bad drawings. We know that when we add these forces together, we should get a new force, and that new force, let's write this in, that new force needs to be upwards with a magnitude of 120 newtons. So can we use this to figure out T? We want to find the magnitude of the tension. We know from the previous question, the magnitude of the resultant, the magnitude of what we get if we add them both together will be 120, because it's got to balance this way. So how can we figure out T from this? Good, it's Pythagoras again. Now, it's not quite how we used it before, because this time we've been given one of the bigger sides. So we know that T squared plus 70 squared is equal to 120 squared. So we know T is equal to the square root of 120 squared minus 70 squared. And that's definitely one for the calculator. So T should be equal to around 97 newtons. Good. And that is in fact the entire answer. Good. Okay, just out of interest, bonus question. How do I know that the resultant of these two forces, this T here and this 70 here, how do I know that their resultant has no horizontal component? No worries. Yeah, they must cancel out because this thing is in equilibrium. There's no other horizontal forces going on in this diagram. So if this thing is stationary, there's no resultant force in the horizontal direction. They must balance out in the horizontal direction. Nice. Good. Absolutely right. Well done. Okay, so thanks very much, everyone, for coming to the session. It was really good to see all of your answers, and it's really useful for me because I can see people are getting things, and it helps us kind of work together and get the answer. So that was great. Really good engagement. It was a fantastic session. Thank you. Stage light isn't moving sideways. Exactly right. Good. Yeah, nice. So I remember I promised at the start that there was going to be a coupon that we'd give away. So we will give the coupon, but first of all, I just want to give you a walkthrough through our SnapRevise website. So at SnapRevise, we've been putting together, as you can see here, all sorts of video courses and content to try and help you get through your A-levels. So we just want to plug that now and show you a bit of what we've been doing. So I'll just bring this over now. And yeah, if you stick around to the end, we've got a coupon code for you. So coupon code. There we go. So this is the SnapRevise website. Looks just like I was kind of showing before. And so SnapRevise is a series of online courses for all of the sorts of different subjects you might be doing at A-level and GCSE. Well, not all of them, but loads of them. So we've got, for example, your maths, your biology, your chemistry, your physics. I'll give you a bit of a look at our physics course. So I'm going to view my courses, and I don't just have the physics course here because I wanted to take a look at maths as well. I also was going to take a look at psychology, but I only got the trial at the moment. So if I go into physics, I learn a couple of things. So the physics course isn't just a kind of a content or like a video book where you click on some things and you get some videos. It's a lot more than that. So the main idea is to try and guide and streamline your learning so that you're only learning the bits that you really need to be doing. So the first part of the course is to work on a quiz. So we're in year 12. Let's see if we can find a quiz on the stuff that we've just been talking about. Here we go. Which one of these looks good? Newton's laws. Equilibrium of forces looks perfect, actually. Good. Okay. So we get an opportunity to start the quiz. Now, lots of websites have quizzes. Lots of websites have online content. The idea of this course is to use the quiz to make a course that's personalized to you. So we'll have a go at some questions. Let's see this first one. You can try and help me out. You're standing on the floor of your room. Which of the following statements is true about the normal contact force? The normal contact force is going to be equal to the weight, but point upwards. Good. Good stuff. Okay. So we can have a go at a couple more questions. Sorry about that. Good. Okay. So we can just have a guess at a couple of these and see how we get on. My computer nearly crashed out. So, okay, apologies for that. So far I've been doing a bit too well. I've got the first few all correct. So let's try and get some wrong. Good stuff. So as you can see, they're pretty decent questions and they kind of go through all the span of the stuff that you want to learn. And there's a good reason for this. We really want to cover everything so we can get the next bit of this course right. So let's see how many we're looking at. Which of the following objects is not in equilibrium? Let's have a go at this one. Parachutist at terminal velocity, that's equilibrium. Seesaw moving around its pivot. Well, I guess this one. Yeah, cool. Okay, we'll have a go at a couple more. We should be close to the end. And here's where the good stuff happens. So, good. So we call this smart adaptive learning. Oh my God, I chose a long quiz. Fine. We're nearly there. Oh, these nasty ones. Good. Okay, I got 35%. So maybe not my best quiz ever. Well, not the worst one I've done, actually. I mean, I got like 11 on one of them, and then it was a bit hard because SnapRevise just said I needed to check everything, which is chill too. Okay, so SnapRevise tells me I got 35%, fine, and it gives me a bit of a breakdown. Tells me what I know and what I don't. Now, this would be great already. This would be useful, and you could go away and just try and focus on the stuff on the right-hand side. But SnapRevise already has a course, and SnapRevise can do this for you. So now I clicked on go to the course, and now there's a series of videos available to me. The ones highlighted in green are ones I don't need to watch, and the sections highlighted in green are sections that I don't need to watch. So now I don't need to waste my time looking at stuff that I already know. And instead, I can just focus on the stuff that I'm struggling with. So here I clicked on one of the videos highlighted in orange. And this suggested this is one of the videos that SnapRevise reckons this would be really beneficial for me to look at this again. And even inside the video, they kind of said, well, you got the question on tension right. So you don't need to learn the tension bit again. You do need to learn about tension when you're on a slope. So why don't you just go straight to this bit of the video? So then I can go straight to this bit of the video and learn just about tension on a slope. Good. Okay. So we're really happy with the service. It's working really well. You can go through these videos and you can learn all the sorts of stuff that SnapRevise thinks that you need to learn based on how you're doing so far. At the end of it, there's also exam questions. These exam questions are great. They're not just an exam question and a mark scheme. They are a walkthrough by one of our tutors at SnapRevise. So we look through the question ourselves and we try and put together a video where we explain not just the answer, but how we personally would get to the answer and how we would approach this question in an exam. So alongside this, we put together these exam packs and revision guides for you, and we let you know how far through our courses you are. So I'll just give you a little look at our plans. So there's a few different kind of levels that you can go for here. We had this idea. We thought tutors are kind of a very inaccessible idea. A private tutor is something that people can have if they can afford £50 for an hour. Like tutors can cost around this much. So we thought, what if we take that kind of service and we try and make it more accessible and try and improve the price. So we thought, instead of £50 an hour, why don't we come up with 3 plans for a month? They are respectively £10 a month, £30 a month, and £50 a month. And we're going to try and recreate the experience of having a tutor. So first of all, we had these kind of tutor style teaching videos. So these are our bite-sized teaching videos, the exam walkthrough videos where we explain how we would do a question, and some revision guides. So this you can get for £10 a month. For £30 a month, not only do you have access to that stuff, but you have access to these quizzes, so the idea of these quizzes is to help you streamline your learning and essentially, hopefully, meaning that you spend less time actually doing revision because you can focus on just the bits that you need to look at. Good. Okay, so alongside these smart adaptive learning and self-marking quizzes, which we try and use to try and help you just focus on the bits you need to do, we also have predicted exam packs where we put together lists of exam questions which we think are the sorts of things that are likely to be asked. Now, finally, there's the kind of web class option, the ultimate option. So here we want to try and recreate everything that there is about a private tutor at a way more affordable cost. So I'm currently doing an extra 6 sessions a week on Snap Revise, web classes like this. A couple of them are drop-in tutor classes. So that means you can just come in with questions that you have, exam questions that you're stuck on, or just general questions you have about physics. And we can discuss them together as a group, and I guide us through them and we get to the answer together. Not only that, but we also have some web class videos which are a bit more like this, where we have a specific lesson that we want to go through. And again, when people are stuck, we can kind of discuss together as a group and try and work through it together. So the idea of the ultimate package is to recreate the idea of a private tutor at a way more affordable cost. So we're really happy with these plans. And thanks, obviously there's a chance for a free trial here, so go for that. If you're interested in the coupon, then we have a coupon for a discount for today, and this code will work for today only. So take a look at this code. Now, here are the future sessions coming up on YouTube, which we're looking forward to doing as well. And here is the coupon. So thanks very much for coming, and let me know if any of you have any questions. So yeah, thanks very much for coming to the session. We really enjoyed that. And hopefully see you at the next YouTube session, and maybe even inside Snap Revise. Cool, yeah, thank you for coming. That's a really good session. Thanks for posting all your answers. It's really helpful as well. Oh, no worries. Thank you very much for coming. Cheers. Okay, I think if there's no more questions, then we'll end the stream there. Thanks again, everyone, for coming, and see you in the future. Great. Catch you later. Bye.